All right. Good morning, everyone. Welcome back to the class. Yesterday we have learned a lot from Professor Natapong, and today also we will learn more and deeper. And before we start the lesson today, I would like to inform you that all materials that presented by Professor Natapong yesterday and also we will be presented today are already on the share folder and it's already on the chat box. Please go check and download all the materials. So, as most of the participants already here, I think we can start the class now. And without further ado, I will pass the floor to one and only Professor Natapong. Over to you, sir.
Thank you very much, and good morning, everyone.
Good morning, sir.
Okay. Before we continue the class materials and the discussions, I would like to go to this clarification first. And I already shared this material with all of you through the chat box, and later we can also upload this one to our share folders. But first thing first, okay, let's take a look at the overview and first understand the big picture and the main motivations why we have to use many models, or why we need at least 4 models for my sessions. I think most of us know the conventional regressions or the OS regressions, or some people call this one as the linear regressions. And it's the basic methodologies to explore the relationship among variables. But this one is the basic technique. So there are a lot of assumptions behind the calculations, and you have to satisfy all of the conditions. And this is the main summary that I would like to share with you. First, the response variable or the dependent variable has to be continuous and normal. So it has to be normally distributed. And data is simple. There is no hierarchy. There is no like the panel structure or the cross-sectional structure inside the data. And there is no heteroscedasticity problem, or is the problem that the independent variable can cause the difference of the variance when you predict the output, or the variance of the output change when you vary the input. And there is no random effect, and this is the issue that we will discuss today. And in this case, we don't need any link functions. And the link function is actually the transformation of the data, or the mapping of the original data to actually it's like we linearize the data, or we transform the distribution of the data. And yesterday we learned this technique, the GLM, the generalized linear model. So I think the title already identify the main tags or the main property of this model, we have to generalize, or we have to transform all properties or all categories of the distribution to be the simple one, or actually like we just simplify the distributions of the data into the normal one, or to try to transform the different characteristic of the distribution into just the normal one, and try to come up with the linear model to predict the results. So this one, like the data set that we used yesterday, and it's actually the practice, or the I think the usual case that we will experience, or we will encounter different distribution of the data. Sometimes we get the binaries data, sometimes we get the counting data, or sometimes we also maybe get the log normal distribution data. So we have to transform the data into the normal distribution first. And again, this methodology cannot handle the cross-sectional data or the hierarchy structure of the data. So we just have the usual data set or usual structure that does not include like the separations across year or across provinces. It's just simple, or the generalized data. And this is the difference. I think the GLM, like we learned yesterday, that we have to handle the different characteristic of the distribution. So the GLM can handle Poisson distribution, binomial distributions, or the maybe log normal distribution. So this allow us to handle many data with many characteristic of the statistical distributions, but still it cannot handle the random effects or the fixed effects, which will be included in the cross-sectional data, or the hierarchy of the data. And I think this is the main characteristic, or the main features of the GLM. We can select the link functions, or basically it's the transformations. It's like the example that I shared with you yesterday, that if we're doing this one on R, and if we use the GLM functions on R, you can identify this transformation. You can select the options of this link function to transform the data, or the distribution of the data into the normal one, or into the linearized forms. So I think this is the most important and the main advantage of using GLM. And again, I would like to share with you that in the regression analysis, we would like to obtain the error term, or the residual that follow the theory or follow the assumptions of the normal distribution. And all of these four methodologies are the transformations, and the is like the extension of the OLS model that allow us to handle different characteristic of data. We can handle the cross-sectional data. We can handle different statistical distribution of the data. But at the end, we want to achieve just one target, which is the normal distribution of the residue. Okay, I think maybe we can just come up with the simple explanation why we need this four model, or maybe we can use more advanced technique that go beyond these four methodologies. But anyway, either you use GLM, LMM, or the GLMM, or all of the main purpose, or the final achievement is actually to obtain the residual that becomes normal distributions is follow the theory that we have normally distributed residual. The mean of the residual is 0. The residual has no autocorrelation, and residual has no the heteroscedasticity structure, which means that it is randomly distributed. It's totally the randomized values. There is no pattern left inside the data of the residuals. And again, first we can use GLM to modify the data, and we can use the link function or the option in GLM to transform the data. And again, we can change or we can map the different distribution of data to perform linear regression by using this link function, or actually is the option in the GLM commands on R. But in addition to GLM, we can use LMM model to handle the hierarchy data, or it's actually the cross-sectional data. And in some field of study, like economics, we call this one as the panel data. Some of you might have studied, or some of you already know the panel regression or panel data. LMM is actually the same methodology, or it's based on the same theoretical foundations. We have to use this new specification to handle this data, which is the cross-sectional data, and we need to provide the intercept term for a specific group of the data, and we will explore the example in this exercise and in this class. But again, for the LMM, we still assume that the dependent variable is still continuous and is also normally distributed. And we assume that the error term, finally we achieve the final final goal, or the final objective, which is the normal distribution of the residual. But I think the main feature or the important characteristic of the LLM is the structure of the equation, or the form of the methodology that allow us to come up with different intercept. Okay, it's not only just one intercept term, but we can provide individual intercept to the specific groups of the data, and we will explore the example later. And still, there is no the transformation or the link function for the LMMs. And the last one for my session is GLMM. So I think if we look at the comparison here, GLMM is the extension of LMM, and I think you may guess from the title. We have this term here, which is generalized. So GLMM is the generalized form of LMM, and then you can quickly expect that it's actually include this modification, or it's actually includes these modifications, which is the options to do the transformation. So it's actually similar to the case of OLS and GLM, because OLS is the LM, or the linear regression model, and GLM allow us to generalize our category of the distribution of the data. So it's follow the same approach that we can extend the original form with the transformation with the link function that allow us to select the option to transform the data. So for today, LMM can handle only the normal distributions, or is assume that all the data are normally distributed. It cannot handle binary data. It cannot handle the like Poisson distributions or binomial distributions or the log linear distributions. If you have those characteristics, if you have the data that perform or is actually have the non-normal distribution, you need GLMM, and you need to do these selections. You have to select these options to transform those spatial distributions. Okay, so I think this material could be very useful, and it will be like the main summary for us, which model should be more appropriate to our works. And again, I would like to emphasize that how can we select the model? How can we come up with the criteria to choose the model? I think that the ultimate target is to achieve the normal distribution of the residual. So any model that can finally give you the residual that become normally distributed and is follow the theory, has this zero mean, it has no autocorrelation, it has no heteroscedasticity. If you can apply any of these four models, and you can finally achieve those targets, that is the best model for you, or this is actually a set of the criteria for you. So this one I already provide the summary, but I think this table can share. I think it can facilitate us with the succinct informations and also the main characteristic of each model. But later you will see some explanation for each one. Okay, so let's start with the first material for today. Okay, so this is RMM. So I still use the materials that produced by the same research institute in Canada. So it's the Quebec Center for Biodiversity Science. And you can go to this link and download and also obtain all materials, which is the original one. But for this workshop, I just selected the main contexts that are related to our main objective or to the topic of our workshop. But if you go to the original website and download the original data and original code, you will see more detail and more extensions of the examples and the techniques that are already distributed in this link. And yeah, again, I would like to acknowledge the contribution of the expert team who produced these original materials. This is the list of the experts who produce the original data and original materials. Okay, first thing first, let's start with the main motivations. It's actually started or motivated by the data, the structure of the data. Let's assume that now we are maybe the researcher in the Fishery Institute, that we try to understand like the variations of the marine biologies, and we collect the data from 6 lakes. Okay, so now we are assume that we are marine biologists, and we have to go to each lake and we have to sampling the fish in each lake. So you can imagine that now we have to handle multi-dimensional data because we have data from 6 lakes, and each lake has a specific species of the fish. And for each fish that we captures, we just want to collect 2 properties of each fish, which is the length and the tropics positions. So it's actually the geolocations in the lake. So we have just 2 data for each fish, but also we have a category of the fish, which is the species of each ones. And also we do the data collection. We sampling the data from maybe the lakes in that region. Totally, we have 6 locations or 6 lakes here. So if you okay, let's take a look at the data first, because I already uploaded the data, and let's take a look at the data. And this is the data set. Okay, I already uploaded the data, and you can download this one from our share folders. So this is the first lake. Okay, and then we capture 3 species of the fish in that lake. And as I mentioned earlier, is that we have the length of the fish, and also the trophical positions of the fish. And then we go to the next one, the second lake, and then we collect the data. We capture also 3 species of fish, and then we measure the length of the fish, and then we also collect the same information, the trophical positions, and we repeat this one, this data collection until the last location, the last lake, or the 6th lake. And still, we have to sampling or capture at least the same number of the species. So we collected 3 species of the fish in this lake. Okay, so actually we have the cross-sectional data, or hierarchy data. Some field of study call this one as the panel data or the cross-sectional data. So we have first the category of the lake, like we have 6 lakes. And second, we have the category of the fish. And then we have the individual information for each fish, which is the length of that fish. And also the second individual informations, which is the trophical positions. And actually, if you don't care about the category, we don't care about the lake, we don't care about the species of the fish, yeah, you can ignore this data, or you can ignore these categorizations, and then we can just use these informations. But actually, the categorizations, which is the lake and the species, allow us to explain more detail, and we can also come up with a better model. And again, I would like to share with you with the simple conclusion or the simplifications of these motivations. If we ignore the lakes and the fish species, and we just run the simple regression based on this pairwise relationship, yes, you get the significant coefficients. But if you look at the residual, if you explore the property of the residuals, you will come up with the I think the characteristic that do not satisfy the conditions or the requirement, because we need normally distributed residual. We prefer zero means residual. We prefer no autocorrelations. We prefer no heteroscedasticity. And yeah, if we ignore the information about the lake and the fish species, we cannot obtain the normal distribution of the residual. Okay, so I think this is the simple explanations why we need to use the LMM methodologies, because we cannot ignore the classification or the categorization inside this data set. We cannot just throw away the lake information. We cannot throw away the fish species. We have to use them, and this information allow us to achieve the better result, is allow us to finally get the residual that is very close to the ideal properties. Okay, and for today, I would like to share with you the other example is actually my honestly is my ongoing project, and I are still working on this one. It's still my unfinished work. It's actually the COVID-19 data set. And I can share the data with you through the chat box as well. So this is the data set. And also I would like to share the code, but we will do this exercise later. First, we have to start with the Canadian example first, or the fish and the lake example. But okay, let's take a look at the data. This is the actual data, and actually I obtained all of this data from the open source material or the open source platform. So I think I didn't violate any copyright issues. And okay, let's take a look at the data. I have actually this is the monthly data. So this is the average number of the COVID-19 cases. So first we have the monthly indicators in 2020 and 2021, and we have the provincial ID number in Thailand, and then we have the name of the province. And I obtained this indicator from Google Earth engines is the free data sources. It's the open satellite data source that you can download. You can extract satellite data from that service. So I obtain the informations about the pollutions like nitrogen dioxide, carbon monoxide, and also sulfur dioxide, and then I come up with the average change, the monthly change of these indicators. And then I have the nighttime light density in each province in each month. And this is the monthly change or the monthly difference. And the last one is the COVID-19 cases. So this is the change. And actually, I did the transformation already. I did the logarithm transformations. First, I transform all of the number into the logarithm scale. And second, I did the difference, the monthly difference. So this is the number that show the change of each indicator from the previous month. Okay, so this is the data set that we will use as the example for the exercise today. And I hope this will give you the idea that it's similar to the fish data, but now the categorization is different. I have the monthly timestamp here. This is the monthly data, the monthly average of each indicators, and then I have location, which is the province in Thailand. I have both the numerical ID number for each province, and this is the name of the province. And then I have 5 indicators that are the air pollutions that I obtained from Google Earth engines. And I have the national statistic of the COVID-19 cases. And this is the open data you can download from the website of the Ministry of Public Health in Thailand. Okay, so again, I would like to explore the relationship between COVID-19 cases and the pollutions or the nighttime light, because the higher the number of the cases, the lower the economic activities. So I expect that if I do the pairwise regression, is I explore the relationship between COVID-19 and nighttime light, I should obtain the negative correlations or the negative coefficients, because more cases of the COVID-19 patients, you will have less number of the activities or the mobility in that province. Okay, so this is the example, but we will see the problem. Honestly, it's still unfinished work, and I have to do more like data cleaning and some adjustment of the data set here. But we will learn together today. Okay, so feel free to use this data. All of them are obtained from open sources. Okay, let's take a look at the material. Let's go back to the Quebec research centers. Okay, and again, we have for the first example, we have the fish data. We survey the fish in 6 lakes, and then if we just explore the raw data, we will get something like this. The trophic positions of the fish and the length of the fish, and then you will get the distribution of the data like this one. But maybe we can categorize the data. First, we can categorize the data by using species. because we try to sampling 3 species in each lake, so we can create these partitions, and then we come up with this one, which is the partitions of the fish species. Okay, here. I think this is a better representations because the first species has the short length, the second species has the medium length, and then I think the last one has a longer length. So we can have a deeper understanding about the distribution of the data that is actually based on the species of the fish. And then we can alternatively categorize the data, and now it's based on the lake, the location of the fish. So we have 6 lakes here, and I think we can have a quick look at quick comparison. It looks like the last one, the last lake of the 6 lakes has like the higher length of the fish size. Like the fish in this lake is bigger than other lakes. Okay, and I think yes, this is the first exploration of our data, and I think it's very important when we have the data. The first thing that we have to do is to explore the data, try to observe and try to understand how the data look like. And in this case, definitely we need we cannot just use simple regression. We need the GLMM regression or the mixed model, because now we have 2 categories of the data that I introduced earlier. We have 3 species and we have 6 lakes, and each category also affects the characteristic of the fish, which is the length of the fish. So this one is called the hierarchical structures. Yeah, in some field of study, call this one as the cross-sectional data. Some field of study call this one as the panel data. But I think yeah, there are the synonyms. There are the similar characteristic of the data structure, and we can use 2 strategy to analyze the data. First, you can run the regression separately, either based on the lake or based on species, or you can just ignore it, like what I shared with you earlier. We ignore the categorizations. We just use the numerical data. We don't care about the lake and the species. Okay. So we have to strategy to handle this one. And first one, we have to separately run the regression. So we have to first pick the first species in the first lake and run the regressions. And then you have to repeat the same process until the last lake and the last species. That is quite a tedious work that we have to keep repeating the same regression again and again based on specific lake and specific species. And second one is the technique that I mentioned earlier, that we just ignore the lake and species. We just pull the data and run the regressions. Okay. But again, the problem is the results that we will obtain. Even though we can get the statistically significant coefficients, because we are interested in the relationship between the size of the fish, or the length of the fish, and the trophic position of the fish. And I think if we just ignore those categories and we just simply run the regression, we get a positive coefficient, and I'm sure that this will be statistically significant. The p-value will be significant. It will be a very low p-values. But again, you will get the anomaly in the residual terms. The residual distribution will not be normal. The residual will contain autocorrelations, and the residual will contain heteroscedasticity problems. And this is the main reasons that we need to control these effects. We have to control the effects from the different species and the effect that caused by the different location, different lake. And that is the main motivation for us to use mixed model. And I think in this case, we can look at the final results. If we would like to, again, we would like to mainly study the relationship between the length of the fish, or actually the size of the fish and the trophic position of the fish. But if we run the regressions, if we ignore the lake, if we ignore the species and we run regression, we will get the straight line here that explain the data. And yes, we will get the intercept term here, and we get the beta one, which is the slope of this line. But the mixed model is the techniques that allow us to create individual line. It can be the individual straight line that explain a specific species, or it can be also the individual line that can specifically identify the property or the relationship in specific lake. So I think this is the main features or the main advantage of using the LMM techniques. You can come up with a specific line that match or that try to fit the approximation with the specific characteristic or specific category of the data. Okay, so like the first one, if you look at the first example, the black line is like the pool data results that we ignore the detail of the lake and species, then you get the black line, which is the average results. But we can be more specific, right? We can create another line that represent this relationship for species 3. And yes, we can create another line that individually match the characteristic of the second species. And then we get the blue line that also individually fit the data of the first species. And okay, we have to look at the specific detail here that all 3 lines or 4 lines that we have here share the same slope. You see that it's actually the parallel line here, but the difference is the intercept terms. So basically, we create the individual line for individual species, but all species remain share the same slope. The difference is the intercept term. And this is the case of the fixed effects. So the fixed effects will use the same slope for all categories, but it will create the individual intercept term for individual categories. Okay, so this is the case of the fixed effects. But in the case of random effects, we can identify the distributions of the intercept term, and we assume that the deviations or the distribution of the intercept term also follow the normal distributions. Okay, so this is the difference between the fixed effects and random effects. I think in this case, we can use the command on R to create the LMM regressions, and the final result will give us the model that show the intercept and the slope of the line. But for the fixed effect, the intercept term will be individually assigned, and we don't care about the distribution of the intercept term. But for the the random effects, we assume that the distribution of the intercept term will follow the normal one, the normal distribution. And the second assumption is that the pool regressions or the intercept terms of the pool case or the case that we don't care, the lake and the species will be the mean of this distribution. And the intercept term of specific species will be distributed around this mean, around the black line or the black intercept, which is the average one or the pool data intercept terms. So this is the specific characteristic of the fixed effects and random effects that we try to come up with the individual line for specific species or individual line for specific lake. But we can ignore the distributions of the intercept terms, like the case of the fixed effects. But in the case of random effect, we still impose the restriction or the characteristic of the intercept term, and we try to assume that the distribution of intercept follow normal distribution, and the mean is actually the intercept term of the pool data. And based on this setup or this assumption, we can go further. We can have the alternative specifications. It's not only just the individual intercept term, but the model allow us to do the individual slope. So in the alternative setup or alternative specification of the model, you can come up with the assumptions of the slope that each species or each lake can has its own slope. And for the random effects, we assume that the distribution of slope still follow the normal one, the normal distribution. And the mean of the slope here is the average or the slope of the pool data, the slope of the data set that we ignore categorizations. Okay, so I think this is the case that we can impose these conditions, and R can do this one. The package on R can estimate the distribution of the slope and the distribution of the intercept term if we select the options to allow the package to do this analysis. So let's take a look at the code first and also the data set. Let's go to R. Okay, this is R, and you have to open the code that I share with you. Is the code number 3, which is the GLMM code. Okay, it's this one. Okay, so this is the code for our exercise. And again, you have to install these packages. If you use the latest version of RStudio, it will automatically recognize this command, and it will automatically install all of these packages. Or you can just do it manually. You can highlight this section of the code and run the code. I think it will take maybe 3 to 5 minutes to complete these installations. So we have to wait until the process is finished. Okay, my computer already finished the installations, and I got one questions about the difference between fixed effect and random effect. So may I hold the questions, but I come back to explain later when we run the model on the code. But first thing first, just start with the installation of the packages, and then include the data, and also run the basic like the data exploration first, and then we will run the model, and then I will explain the difference between two models. First, after we already finished this installation, then you have to activate this part of the code to include all packages. Right? Okay, we already included the packages. Then we have to import the data. So in this example, we will use the Fitch data, the Fitch survey data from Canada. And this is the title of the data set. And please, okay, ignore this line, because you will save the location of, sorry, you will save the file in different location on your local computers. So I think I will do this one manually. I will go to import data here, this box. We will import the data, which is the CSV format. So we'll select the first option. We will import the text-based data. And then the data is not here. The data is here. So it's this one. And I select import. Then we have the data set here, which we opened earlier. We opened this file earlier. And then we can run the code. First, in this example, they rename the data set. So originally, the data set is titled based on the file names. And then R recognize this one as this data set, but you can rename the data set here, or actually you create the replica of this data set is the identical one, but now we title this one as fitch.data. So we can highlight and run this line. So you will see that now we have two data sets. We have the fitch data and we have the original data, and both are identical. And then we can create the plot. So I would like to highlight all of these sections. So I would like to highlight these sections from line 118 to line 82. These are the sections that will plot the charts. And when we run the code, we will get actually three pictures. The first picture is let me enlarge. The first picture is the distribution of the data, all data, because basically in this example, we want to understand the relationship between the size of the fish or the length of the fish, which is the horizontal axis. And we want to understand this correlations or this relationship with the trophic position, which is the vertical axis here. And this is the data for all lakes and all species. But in the second chart, we try to categorize the data. So we separate the data into three sets, and it's based on specific species. So the first box is the partition of the data that based on the first species. And then we have the second set that based on the second species. And the last box is the partition of the data that based on the last species. And also we can do the alternative representations, and it's the illustrations of this data based on lake. So we come up with 6 boxes of the plots that represent the relationship in each lake. It's between the length of the fish and the tropical locations of the fish. So this plot allows us to understand the distribution of the data, what the data look like when we categorize the data based on species and based on the lake. Then we go back to the code again. Honestly, I think it's not necessary because this is it's the same process or is like the activation that repeated again. We can ignore this part because we already read the data from the CSV file earlier, and we already renamed the data, or we create the replica of the data already. So I will ignore both lines here. And we can activate this one. It's similar to the command that we did earlier yesterday, that is will explore the basic characteristic of the data structure. So this is the, it's like we look at the data frames, which show the row and the columns of the data. So in this case, we have 4 variables, and we have 180 observations. And for the next one, we can activate this code, and this will show the table of the data. And for the next one, we can generate the chart that show the histogram of the data. So if you activate these blocks of the code, you will get the result on the right-hand side on this result plot as the statistical distribution of our main variable, which is the length of the fish and the trophic positions of the fish. Honestly, I think it's not normal. For this, the first one, the length of the fish is not normal, and it's not normally distributed. But okay, in this exercise, it is recommended that we have to scale the data, or we have to normalize data. So we actually compute the disease score, or the deviation from the mean that divided by the standard deviations. So basically we standardize the raw data. Okay, so the first data that we will do the standardized process is the length of the fish. So this is the code that will compute the output that will be the standardized value of the length of the fish. You can activate this line. So it will measure the length of the fish based on its deviation from the mean. So basically, yes, we standardize the data. And the second one is the alternative approach, that you don't need to do the first technique. You just use the scale commands, and this will automatically standardize your data. So the second variable that we are interested in is TP, the trophic positions. So we can use this command to standardize these values. So in this example, we will first pre-process the data, and we standardize both of them. And then, sorry. The next one is, I think, the quick calculations that we can use the command that we did yesterday. This is LM, which is the simple linear model. This is the simple ORS, simple regressions. So we use this simple command to compute the simple regressions, and it's the relationship between the length of the fish, which is the standardized value, and the trophic position of the fish, which also standardized already. And the data source is the fish data that we have here. We already imported this data. And then we have to do the residual analysis again. Like we have to look at the distribution of the residue, and we can look at the scarcity property of the residue, which is the variance of the residue. Is the variance stable or not. Okay, so we can activate this section of the code and do the simple linear regressions. So I think the first one for these sections, we ignore the lake, we ignore the species, we just do the simple regression based on pool data. We combine all the data and do the simple regression here. And this is the, oops, CTP not found. CTP topic positions. What happened to this one? Topic positions. CTP is disappeared. Check the data. Yeah, it's CTP is not included, so I didn't calculate CTP. Okay, sorry. And then we can run this portion of the code. Yes, we get these results. So we have the distribution of the residue. So the first chart on the left is the distribution of the residue based on species of the fish. So we have the different distribution of the residue that vary or is based on the specific species of the fish. And also on the right-hand side, we have another plots that show the distribution of the residue based on the lake, based on the location of the fish. So this is the main motivations that we can improve the result of the regression. We can obtain a better residual distribution by using the LMM technique. So next one, we will have the code for running the LMM. So the commands will be slightly changed. If you look at the code box here, the command is LMER, which is the command to run LMM. And then you can first run the first LMM model. And then you can modify this basic model with different characteristic or different setup. So you can, again, this is the case of the fixed effects and random effects characteristic that we can impose different options to control the slope and the intercept terms. Okay, so these are the set of the different model that impose different options on the distribution of the intercept term and the slope terms. Okay, let's go to the explanation, and thank you for the questions. So I think it's related to the code that we are doing now. So for the fixed effects will try to generate. Okay, let me go to this page. Fixed effects will generate the line, right? It will generate the line specifically for each species. Okay, you can impose different option on the code that we can create the line specifically based on the individual lake, or you can create the line specifically based on individual species of the fish. But okay, in this case, if we would like to create a specific line that will fit the data of a specific species, you will get 3 lines, or actually 4 lines, right? And all 4 lines use the same slope. You will get parallel lines here, 4 parallel lines, and you will get different intercept terms. And for the fixed effect, we don't care about the distribution patterns of the intercept terms. Okay. It's the code will try to match the line with specific group of species of the fish, and the code will try to minimize the residual for each species. So that is the main objective function for the code. Basically, in mathematics, it's try to do minimizations. It's try to minimize the residual for each species. And it will keep all line parallels. It's try to come up with the same slope for all lines, but use different intercept term. And the value of the intercept term is based on the optimization or the minimization problems. But for the random effects, we assume that the distribution of the intercept values, because now we have, this is a simple example, so we have just 3 lines, right? 3 intercept term, and it's actually follow the normal distribution patterns, and is scattering around the mean value, and the mean value is the intercept term for the line of the pool data. It's actually the line for the first model that we did earlier is the simple LM model, so simple linear regression model that we ignore the lake and the species. Okay, so this is the case of the random effects that we impose the distribution properties of the intercept terms. And so in the LMM regression, you can use both. You can try fixed effect, you can try random effects, or you can first start with the simple LM model. And the criteria to select the best model is the quality of the residual. Which model that can generate the best residual, which is really close to the ideal property of the residual, which is normal distribution, that would be the best model for you. But there is another the technical issue about the random effect and fixed effect, and it's about the degree of freedom. I don't want to go deeper into detail, but if you are concerns about the degree of freedom, if we have a small number of the observations, we care about the degree of freedoms. The fixed effect will consume, or it will generate a lot of endogenous variable, which is the individual intercept terms, and that will create a small degree of freedom, right? But for the random effects, it's best for the small samples or the small observations data that we can save the number of the degree of freedom, because it's imposed these assumptions. So you can have a better degree of freedom for your estimations. So I think it depends. If you have a big data set, you don't have to care about degree of freedom. we have enough number of observations that allow us to work with the degree of freedoms and anyways, but if you have a small sample size, maybe random effect will be better. You create more efficient output, but anyways, still the quality of the regression, the quality of your model depends on the quality of your residual. And again, you have to use the criteria of the normal distribution to test and to select the model. And like I introduced earlier, that we can go further, we can extend the model, and we can create individual slope for individual characteristic like this one, like this example, that we can come up with the model that create a different slope and different intercept for different species. And we can also impose the same property for the distribution of the slope, that we can impose the normal distribution as well. And in this one, in this slides, it's also emphasize the same issue that I mentioned earlier, that if the degree of freedom is your main concerns of the estimations, maybe random effect is better, but you have, if you already have a big observation, you have a big data set, you do not have to worry about the degree of freedoms. Okay, so I hope this will give you the basic idea of the GLMM regressions. And specifically for this exercise, you can come up with this first model, which is the output that give you 4 lines, which is the first pool data. The black line is the pool data. It generally produced by the LM regressions. But with the GLMM regression, if you select a species as the criteria, then the model will generate 3 parallel lines that will explain the data that will fit the data specifically for each species. So now you have a different model or different straight line that explain the relationship specifically for each species. Or alternatively, if you use the lake as the main characteristic, or we use the lake as the categorizations, now we have 7 lines, right? We have 7 straight lines. And the main one, or the first one, is the black line, which is the average one, which is the result from our LM model, the simple model. But we can use GLMM model and impose the options on the lake specifications. Then the model will generate 6 lines, and each line is the best estimate, or is the linear model for each lake. So now each lake will have its own individual model or individual equation that explain the relationship between the fish size or the fish length and the fish trophic position in that lake. So it depends on your purpose of study. If you concentrate on species, then you can impose this option, and you can put the commands and then select the option that we will create the line, the individual line for a specific species. Or if you are interested in the location, you want to understand the relationship between these 2 variables in each lake, then you can alternatively impose the commands or impose the option to create the line specifically for each lake, and then you come up with these results. And again, for the techniques that we can go further and then impose the different slope for specific species. And one concern is about the the I think it's the slope, the range of the slope. If your data is very big and is maybe include the variations across species, then you will get the range of the line or the range of the parallel lines that will be very big because it will captures specific characteristic for specific species, and all species are much different. Oops. Any technical problems, or is the break time? Okay.
No, no, you
Yeah, I
can
think it's a
continue.
break time. It's good time
Uh,
to take a break. So let's have a break, right? And then we will resume the class. Okay.
Okay, then
Yeah.
now we can have a break and be back
Yeah,
to
we'll come back later. Yeah.
yeah,
Thank you.
back to the class at 10:30 maybe. Yeah.
Yes. Okay. See you. Yes.
All right, it's 10:30 already. I think we can start again the session. Is Professor Ratapong already back to the class?
Okay, let's resume the class.
Yeah, apologize for the previous.
That's okay. I
Yeah.
hope you enjoy the fish data.
Yeah, so sorry, Professor. Yeah, we have a drop in a connection suddenly, but everything is okay now. Over to you, sir.
Okay, thank you very much. And so let's resume our discussion. So actually, we have also this concern of actually is the heterogeneity, or it's actually the variety of the value across species. And it can measure as the ICC, or is the ratio of these variations. So it's based on the ratio of the variance. So yeah, if you have the variation across species, or the variation across the lake, and the variation is big, then you should impose the fixed effects or the random effects on that specific category. So in the code, in the GLM functions of R, we can also compute the ICC to also make the decision about the option that we should use in this LLM model. So if ICC is very, very low, you may ignore the case of using specific intercept. And that will also involve the concern about the degree of freedoms as well, that will give you more degree of freedom in your analysis. And so ICC will allow you to measure the variations of the intercept term, and that will also help you to make decisions about doing the individual intercept term for each categories. Okay, so like I discussed earlier, maybe the fish in its lake are much similar, it's really alike. So you don't need the intercept term across the lake. Okay, that will save the degree of freedom, and it will lower the complication in your analysis. But yeah, if you have the case of the variations, then you have ICC. And that also create another problem of the confidence intervals when you compute the t-stat of the slope. Okay, so this is the concern on the ICC that will affect your decision on selecting the criteria of the categorizations. But okay, anyway, so in this case, we have the fish data, and we have 4 steps to do the analysis. The first step we did earlier is like the exploration of the data. We try to understand what the data look like, and we try to have like the first glimpse of the data. So it's the basic information that we learned earlier. But okay, let me go back to the mathematical representations. For this data set, we basically would like to understand the relationship between these two data, the size of the fish, or the length of the fish, and the tropical positions of the fish. And then we impose the characteristic of the lake and characteristic of the species into these equations. And the rest of the equation is the residual term. And again, residual term is actually the major criteria to select the model. And in some cases, or if you measure the ICC, maybe the fish across lakes are very alike. They are very similar. You can ignore the intercept term for the lake, right? Or if you have the ICC values for the species, and fish in the same lake are really similar. For all species, they are the same size. then you can ignore this term. You can ignore species, so you don't have to create a specific line for specific species. Okay, so but for the full model, for the full specification of this example, we want to create the line for specific lake and specific species, and that will be the specific intercept term for each one. And again, we actually did this one earlier. We have to import the data, and I shared with you also previously that we have to ignore this slide because we need to import the data manually. If you use this command, it will go to this folder and import the data. And then we can use the str command to take a look at the structure of the data, the data frame of this example. And then you can use the table commands to take a look at the distribution of the data. And then we can use the histogram command to generate the histogram of our key variable, because we are interested in the fish length and trophic position of the fish. So these two lines of the commands will generate the histogram of each variable. And we can also use the correlation test to explore the correlation between two variables. And this is the process that I introduced earlier, that we can use the command to standardize the data. So this will reduce the variation of the data. First, you can use this line of the code to standardize the data. Or if you prefer short terms, you can use the scale commands to standardize the data. And next we have to do the test, and I already activated this slide earlier. So we just do the simple linear regression model using LM commands. And this is a very simple regressions. It shows the regression results between the length and the tropics position of the fish. And then we can analyze the residue of these results. And we can also extend the first analysis and try to look at the distribution of the residue across the species and across the lake. And the results show that the distribution of the residue depends on the category of species, and it also depends on the category of the lake. That is the main motivation that we need to do the LMM, because each lake and each species can change the distribution of the residue. So the residue is not the pure randomized value. It's actually depends on the characteristic of species and lake. Okay, so this is the results that actually we obtained earlier from the activation of the code that show the distribution of residue change when you switch to use a specific group of the species of fish. And also on the right-hand side, it shows that the characteristic of the statistical distribution of the residue change when you control for the lake, or when you specifically compute the value for each lake. So the classification of species and the classification of lake affects the residue. That means the residue is not it's not normal distribution, it's not a randomized value. So we have to take the species and lake into account for this analysis. And then we can use our LME4, which is the library or the package that can do the LRM test. Okay, and we already downloaded and installed this package, and then we can estimate these equations by using this code. And actually, we activated this one earlier, that we would like to understand the relationship between TP, which is the trophical characteristic, trophical position of the fish, and the size of the fish. And it's also based on the particular lake and particular species. And for the options here, or the specification here, you have to identify the data set that we would like to use. And we use these estimation methodologies. And this is the functions that we can change, or we can come up with the different specifications. Okay, so this one is the random effects command by lake. So if you have this preference to use the random effects for lakes, and also is involved is both this intercept term and slope, you can use this command to impose these options. Or if you just want to impose the random effect on the slope only, you can use these options. And you can use the options to allow the effects across the lake. Or you can impose this option as well to allow the interaction across two random effects. And there are two methodology to estimate the coefficients, the REML and ML. ML is the maximum likelihood techniques, and REML is the restricted maximum likelihood methodologies. So finally, if you look at this list of the options, we can do all options, and finally you come up with 8 models. So this is the full list of the possible or the available characteristic or the available specifications of the model. Okay, the first one is just the simple linear model, or the simple ORS model. We ignore the fixed effect and random effects, but the first model, we impose the fixed effects and the random effects for species and lake. Or the second options, we can relax and also allow the intercept and the slope to be varying. Or we can drop the lake and concern only about species. Or we can drop the species and concern only about the lake. Or in the fifth model, we drop the lake and we allow the intercept term and slope to be varying in these results. And alternatively, we can drop species and we allow the intercept and the slope to be varying in this model. And model 7 allow us to impose the flexibility of the intercept and slope for the lake. And the last one is the opposite one, is the alternative setup that we allow the flexibility of the intercept and slope for species. Okay, so this is the full list that allow us to impose different specification on slope and intercept term for either the species of fish or the lakes. And now we come up with the main question, which one is the best? And we can use AIC as the main criteria to select the best model. So AIC is a guide information criteria, is the index that measure the efficiency and the accuracy of the model. So you have to include this library, or you have to include this package to activate the calculation of AIC. And this code allows us to generate the AIC for our egg model, and it will also rank or show the list of the best model. So the lowest AIC is the best one. So you can look at this column and you see that model number 8 is the best one in this example because it's come up with the lowest AIC. And also this one lists the degree of freedom for our analysis as well. So the AIC is, I think, the most popular one for comparing or for using as the criteria to select the model. And yes, our simple LM is the worst one that perform with the lowest one. The basically is the highest value of AIC. Okay. So when you run the model, I think you can just use this code. Okay, you just modify this code and use our model, which basically 9 model, because we include the simple regression here. And then we just, again, rank the size of AIC and select the model based on the lowest value of AIC. Okay, so in this case, it shows that we come up with 2 potential model, either model number 8 or model number 2. Okay, and finally, they select model number 8. Okay. And I think finally we come up with the final results and we select model number 8 as the best one. And yeah, we already selected the model. Then you can check the quality of the model. Again, you can check the residuals, you can check the distribution of the residual. So I think in this example, you come up with a very nice result, right? Because the residual is normally distributed. And I think that there is no pattern inside the residual because this is the example of the result from the scatter plot of the residual. We prefer this one, the first one, because it shows the totally randomized value of the residual. The rest are the cases of the residual distribution that still contain specific patterns, that you have the pattern left inside your residual. So it's not a pure randomized series, or the in physics or in engineering is the white noise is totally randomized. And again, we can use the plot to look at the distribution of the residual. And now with the model number 8, I think we can improve the quality of the residual, because if you compare this one to the first plot that we did earlier, the distribution of the residual change across different species of the fish. But in this case, if you compare 3 categories of the species, these residual are very similar, and the mean of the residual are close to 0. And again, if we use the lake as the main classifications and compare the distributions of the residual across a lake, now is better if we have the improved results, because the mean of the residual are close to 0, and also the variance or standard deviations of the residual are very similar. So we can also do the last test for the residual, and we get the histogram of the residual that we obtained from model number 8. And I think we have a very nice result. The residual is very similar to normal distribution. So this is the validations of the result, and it show that with this specification, with the selections of the lake and the species intercept terms, we can come up with a better or the improved residual, that the residual become like a white noise, or like say the random values here. Okay, the last one is the representations, and we can plot the results. First, we can do the simple plot, like the first one that we did at the beginning, that we just pull the data and plot the data. But this one is different because the plot is based on the result that we estimated from model number 8. And then we can show that we have our results that based on species. So we have a different line based on specific species. And in this case, we use model number 8, and model number 8 give us the best AIC values. So we have a different slope and different intercept term for each species. So you will see that for the first species, we have different intercept and different slope. And for the second and the third one, we have the same slope but different intercept for second and third species. Again, we can alternatively show this result is the estimation of our model, the straight line model that show the straight line specifically for each lake. So we have 6 lakes here. So we have 6 lines that will fit the data, or fit the relationship for each lake. Okay. I hope this will give you the complete example and the complete step of doing the LLM. And let's run the code. I think we left the code earlier before the break. Earlier we are here, and is the results from the residual plot before we use LLM. So the residual is not normally distributed. The characteristic of the residual depends on the species of the fish, and it depends on the lake. And then we can do this one, egg models calculations. We have actually nine specifications. So we can import all of this specification and run our models. And then we can select another section of the code and create the table. So this table will compare the value of AIC, archaic information criteria. If you are interested in this history, Akaike is the leading statistician from Japan. You can Google his name, and he worked in the US. He was deported during World War II back to Japan. And after World War II, the university in the US invited him to go back and to do the research, and he come up with the AIC criteria here. Okay, so it's a very interesting story about him, that his work was interrupted by World War II. But anyways, his contributions allow us to use the AIC as the criteria, and yes, it's identified that model number 8 is the best one because we have the lowest AIC for this model. Then we can because this example try to specifically understand the difference between model number 8 and model number 2. Because these are the best, the top one. top two, but finally they select model number 8. And then after the selection, after we choose model number 8 as the best one, we go back to analyze the residual again. Okay, so we regenerate the residual plot again. So first I think we can, let me select, first we can select this section of the code and run. Then you get the scatter plot of the residual. It's much better than the previous one. It's very randomized. And then we can also generate the plots from this section of the code. And then we have these results. So it's the identical plots that we explored earlier in the PowerPoint. And this confirmed that model number 8 improved the result because the distribution of residual is much better. It's very close to normal distributions. And the difference of the characteristic of the residual across species and across lake are very small. It has lakes, it has less variations across species and lakes. And the last one, we have the historical plot for the residual. And yes, we have the residual distribution, the histogram of residual that look like a normal distributions. And the last part of this example are the code that generate the representations of the results. So the A sections, this is the A sections of the code generate the I think we have to include, maybe you can run all sections, all 3 sections of the code here. I think I didn't run some part of the code. That's why I cannot generate the results. Let's do the complete activations of the last portion of the code here. Run. Okay, yes, finally we can generate the results. So we have pre-chart here, which is the model that we approximated. Is the straight line that try to fit the data, try to show the relationship between the size of the fish and the trophic position of the fish. This is the overall case that we ignore the contribution of the lake and species. And then this one is the first results that we use the categorization of species as the determinant of the slope and intercept. And next we have alternative one that use the lake as the criteria to determine the intercept term and the slope for the line for the model. So these are the results and the step to do the analysis. Okay, so we have limited time, and I would like to move to the next example, which is my own analysis. Actually, is my still ongoing and unfinished works. First thing first, we can clear everything. I will clear the pictures. I will clear the memory of R. I will delete all variable here. Let's say I will close these windows. Save page data. Okay, so I hope you see my screen here. This is the code for Thai data, and basically I just modify some lines of the code of the previous code to analyze my data, and I earlier walk you through the structure of my data. Is the COVID-19 cases in Thailand, is the provincial data, and is the monthly data. So you have two categorizations. You have the province and you have the month inside the data. And I would like to explore the relationship of the satellite indicator that can be related or can be the predictive variable for the COVID-19 cases. And please again ignore this line because we would like to manually import the data. So first we have to go to this Windows, select import dataset and select it from the Excel. And then this is my data, Thailand COVID data. Okay, this is the data. Okay, so it's imported here, already imported. So I think you can have a quick look and you can guess that now we can replicate or we can modify the fish data, but now we will explore the relationship between the COVID-19 values or the COVID-19 cases. And I would like to first use the nighttime light density as the proxy. So we basically explore the relationship between these two variables. And we have the categorizations of the province and the month. So so we first already imported the data. And again, we can run the first block of the code to analyze the data distributions. So I will run the code from this block. Okay, because we have the data that include okay, two dimensions. First, I explore the relationship between nighttime light density and COVID-19. This is the all data set. And then I classify this one as the monthly data. And then the next one is the case of the particular province. Okay, so this is the data based on the provincial categorization, and there are 77 provinces in Thailand. So you have this plot here, 77 provinces. Okay, and we can use the same process to analyze this data. First, we can explore the relationship of the data and the characteristic of the data. But again, if you look at my code, the main modification is the dimension of the classifications. Earlier, we have fish and lake. Now we have time and province. And from the table or from my data, the time will represent the month. And PV is the name of the province. And we can also explore the fundamental of the data here. I run this portion of the code. Why I select these two variables? Because I come up with this result, and I think we should explore the relationship of these two variables. On the left-hand side, we have the histogram. We have the distribution of the change in nighttime light. Is the monthly change of the nighttime light. It looks like the normal distributions. And on the right-hand side, you have the change in the COVID cases, the number of the patients of the COVID-19 cases is cover the period of 2020 and 2021. And it looks like normal distribution too. So I think maybe we should start with this relationship with this pairwise regression between the nighttime light and COVID-19. And then we follow the same step of the calculations. We standardize the data. So this portion of my code just use the same techniques that we can first use this formula to standardize the variable, or we can just do just the short term or the short approach, just use the scale commands, and we can standardize the data. And then we can do the LM tests, or just run the basic regression first and explore the relationship between the this portion will plot the residual. Okay, first we just apply simple regression, and then we plot the residual of this LM, these simple regressions. Okay. And I think we have some anomaly in my residual, especially it's caused by some anomaly of my data, so I have to fix this one. But you will see that the residual is not normally distributed. There is the patterns in the distribution of the residual, and we see the fixed value here. So there are the fixed value, actually the value of 0 cases that cause this constant value here in the residual plots. So I have to clean the data. But anyway, we can use the same technique that previously applied. So we can run 9 models. Yeah, 9 model. So is this the portion here? So we can highlight this code and then activate the calculations, and then we can come up with 9 model. And again, I can create the table to compare the results. So it's actually this section of the code. So we have these results, these comparisons. And this one is different from the case of the fish data. The base model is number 6. Okay, if you look at the size of the AIC Akaike information criteria, model number 6 is the lowest one. Okay, so we select model number 6. Okay, so model number 6 will be the best one will be the selected one, and then we have to go back to analyze the residue of model number 6. So I will run this section of the code to activate the analysis of the residuals. And there are some pattern left inside the residue. So the residue is not normally distributed. It's not the purely randomized value. So this show that even though AIC value show that number 6 is the best model, but I think the quality of my data is not good enough to generate the results that finally come up with the normal distributions of the residue. So I think I stop here in my code. I have to go back to work on my data cleaning and data processings, data pre-processings. Okay, so I would like to share this example with you because we can integrate the data from many sources, and typically we can use the cross-sectional structure to classify some characteristic in the data. Like this one, I have provincial data and I have also monthly statistics. So I finally come up with this cross-sectional structures that becomes the monthly provincial index. But yeah, we will see some anomaly in my residuals. And I think this is the motivation for the next part, which is the last model for us. And it's actually the GLMM. So I introduced earlier today that GLMM is the extension of LMM, and G stand for generalized. So it can handle different distributions of the data. Okay, I switch back to my first PowerPoint here that I introduced at the beginning of today's sessions. Okay, GLMM is the last model for us for our sessions, and I think it's the special characteristic that of the model that allow us to analysis. So we can again modify the LMM to the data that is actually the combinations of different distributions. It can be Poisson distribution, it can be binomial, it can be log normals. So this one is the main advantage of this model. And honestly, I have to work on and try to improve my model with the COVID-19 data set. And definitely, I will try my model on my data with GLMM because the COVID-19 cases is the count numbers. It's actually the Poisson distributions, the maybe the assumption of my first analysis is incorrect. And actually, I have to handle the Poisson distribution. And maybe the GLMM is better for my analysis. Okay, but okay. First thing first, we go back to the sheet again. It's the last set of the material that I prepare, and I already share with you through our drive, to our share drive. And the first one is the PowerPoint. Okay, this one. Again, it's the materials that I modify from first, I would like to acknowledge the expert who produced the original material. And again, I use the material from the same institution. It's the Quebec Center for Biodiversity Science. And you can go to this link to download the original data, original class materials. And this is the first page of the original materials. Okay, I think we learned the case of LM, right? Yesterday, LM to GLM. And today, again, we learn LM, so LMM, and LMM can be extended to GLMM. It's based on the same foundations that we can generalize the model, which means that we can allow a different statistical distribution of the variables in our model. And we need to do the mapping. We need to impose the options to match our model with the specific statistical distribution of the data set. And these materials already share the example, the data set here, which is the flood data set. And in this data set, they found that the number of the flood is the counting numbers and is follow the Poisson distributions. This is one of the main motivation that the GLMM is recommended, because you cannot use just LMM to do the analysis. And I think that the rest of the code are similar to the previous one, to the case of LMM. First, you have to look at the variance of the data and characteristic of the data. And in this case, it shows that the variance of the data and the distributions change when you impose the characteristic of the data. And in this data set, there is the variable that identify the biological characteristic of the fruit. And if you include this biological and also chemical characteristic into this plot, then you get these patterns. So I think there are two main spatial features of this data set. First, the main variable is the total number of the flutes, and is the count, and is follow the Poisson distribution. So it's not normal distributions. Second, the data set include the, it's like categorization or the qualitative variable. So it's include the genotype, the nutrient, and the clippings conditions. So these three characteristics also determine the variance of the data. So I think for the first one is the main motivation that we need the first G, the generalized case, because it's not normal distribution. And this one is the motivation that we need the LMM model, because the data contain the classification or the categorization that also affects the results. It affects the variance of the results and the variance of the residue. But in this case, I think first we have to understand the statistical characteristic of the data, especially the statistical distribution. So you have to check the distributions, and finally they come up with the selection of Poissons. Okay, so we use the same library or the same package on R. Still, we use LME and then we use this command to activate the GLMM calculations. And the total number of float is the dependent variable. And now we have 3 independent variable. And we have also the fixed effects or the random effects that based on 2 categorizations. And this option identify the source of the data. And the last one is I think the most important one that we already specified that we would like to use the case of Poisson distribution as the transformations of the data characteristic or it's like the link functions. I think then you have to check the characteristic of this one, how the categorizations, especially the biological classification of the float affects the variance, and they check this effect and they found that yes, it will affect the distribution of the data, especially the case of the Poisson distributions. So we come up with this command to run the model. Or we can use the Poisson log normal distribution options. And I think the rest is similar to the case of LMM. But in this case, we have special command to run the plots or to generate the result that show the effects of the randoms and the fixed effects selections, because the fixed effects will determine the variation of the intercept terms. So we have the common intercept term here, and we can have the specific intercept term for each categories. And we can also visualize the result from the random effects. And the results will show the variation of the intercept term based on particular specifications of each category. This will show the variation of the intercept terms. Honestly, for me, I think it's very similar to LMM, but first you have to check the distribution of the variable. And like in this example, they already check and they identify that the variable is the Poissons. And then second, this command also include the spatial visualizations that can show the results of the fixed effects, and this can show how each categories can affect the coefficients. Either you use fixed effect or random effect, you can show how each category will affect the intercept terms. Okay, so I think this is the summary of the second example, and we can go to R to run the code. So now if we go back to R, and I have to delete the previous results and previous variables, then I have to import the data and import the code. Okay, so this is the code for our last example. And yeah, for my RStudio is notified that I need to install more packages. So I just click on install. So R is installing the new package. So you have to activate the first part of the code. And again, it's the installation of the packages. Okay, it's already done. It's already finished. And then we can include all of these packages of this library. Okay. Next step, we have to import the data. So we can do it manually. We go to the Windows here and select import dataset. It's the CSV format, so we have to select import from text file, import this one. So yeah, finally, we have this data set. If you take a quick look at the data set, this is quite different from previous exercise that we did earlier. I think most of the example that we did earlier, we have the numerical data. We have this continuous variable. And in this case, we have integer. Most of the data, I think all of the data are integers. And it's also the count data, and it's also include the the qualitative characteristic, like the locations, the status here, the regions. So this is the I think the unique combination of the data, and it's much different from previous example that we did earlier. That we have, I think we have just the count data and the qualitative variable, and we don't have the continuous variable here in this data set. And that is I think the main motivation to use GLMM. And yeah, we can run the code, and it's the visualizations of the data characteristic. I think I will do this one first. And then the next part is uh, the code that will activate the data imports, but we just ignore this code, and we already imported the data. So we can just activate this line to rename the data, to create the replica of the data here. Then we can plot the distributions. Okay, so now we have the result that are identical to the PowerPoint. First, we have the main variable, which is the total number of flutes in each area, in each observations. It's the cloud data, so it's follow the Poisson distribution. And second, results show that the variance or the number of the flutes also related to the category of the biological characteristic. And then we can run the code to, first it will explore the relationship here. Oops, sorry. To check the characteristic of the Poisson distribution. And I think the main part is here, that we will activate the Poisson distributions options with the GLMM model here. So this is the main part of our model. The command that will activate the estimation of the model. And this code will compute or will estimate the first model. But you can, I think, do the most important part is here that we can, again, come up with 6 options to run the model, and we can compare the results. So the code that I just activated generate the results of the coefficients distributions, the intercept coefficients. But again, we can try all possible options for the model. There are 6 possible specifications of the model. So we can run this code to activate all 6 models, and then we can again compare the AIC values. And finally, the AIC comparison show that model number 2 is the best one for this example. So we can select model number 2 as the main predictor or the main estimation for this analysis. Okay, so I think this is the last part of my sessions, and GLMM is the case that allow you to include data set that are not the normal, like not normal distributed data, and you can incorporate more qualitative information, like qualitative classifications. And I think this example is really extreme case that we don't have the continuous value, and most of the data are just the count number and the qualitative characteristic. But still, we can estimate the model. And in this example, we have 6 options to specify the model. And finally, we can compare the AIC values. And in this example, model number 2 is the best one. And then we can finally select model number 2, and we can plot how each characteristic can affect the intercept coefficients. Okay, I hope this is the last part of my example. I'm very sorry that for the last one, I don't have the actual example. I don't have the data set that that is very similar to this one, but hopefully in the future, if I can construct or can integrate some data set that I can share with you, and that could be another example. Thank you very much, everyone.
Thank you, Professor Nat. Now I will go check to all the participants. Is there any question to Professor Nat? Or everything's clear? Because the explanation is very, very clear from Professor Nat. It's really great to hear the explanation, the lesson. So last chance. Any question to Professor Nat? I guess everyone's got your point, Professor. So if no question for now, maybe some of you still need time to digest all the lesson that we learned today and also yesterday. For your information, if you wanna watch again the session for today and yesterday and also last week, you can go check to ASEAN Start YouTube channel. Everything is available on that site. So before we close the session today, I would like to thank Professor Natapong we really appreciate your time despite your busy schedule at the university and also with your research. We do appreciate that. We really grateful to have you and hope can see you again on our last topic on early December.
Thank you very much. My pleasure to work with you, and I'm also looking forward to continuing our collaborations. Actually, I am working on many satellite data and the geographical study, so I hope that I can share the data and techniques with you, not just like computations, but like the
Yeah.
data extraction, data integration with you in the futures. So
Yeah, then we would be
keep in
grateful
touch.
for that, sir.
Please keep in
Oh,
touch. Yes.
sure, yeah. Yeah, so again, thank you so much. Thank you so much to all participants. Thank you so much for Professor Natapong. See you again on the next session. Bye-bye.
Thank you very much. Please take care.